We now define one-sided limits, which is a very useful concept, especially for checking continuity at a point. Since our definition of limit was quite general, we can make quick work out of the definition of one-sided limit. So without further ado, definition. Let f from S to R be a function. Suppose A in R is a limit point of S intersect A infinity. We define limit x going to A plus f of x. This is also denoted f of A plus in many textbooks to be limit x going to A f of x, but not of the function f, just f. What we do is we restrict this function to S intersect A infinity and then take limits. Recall, this stands for restriction to S intersect A infinity. So again, a picture is worth 1,000 proofs. Here it's fairly simple. You have some set S, this is supposed to be the set S, and you're focusing on a point A. Let's say A is here. You want to define, so if A is there, there'll be a problem. So what we'll do is we'll draw a better picture. We have this set S and we are taking the point A here. Okay. Then to define the right hand limit at this point A, which is denoted by limit x going to A plus f of x. So let me just, this is called right hand limit. To define the right hand limit at the point A, what you do is you focus on this portion of the set, restrict f to this portion, then you take the usual limit that you are familiar with. Okay, so because we required only the point A to be an adherent point of a given set to define limit at that point, not an adherent point, we required only the point to be a limit point of the particular set. Our earlier definition of limit can be borrowed and used in this case also. So we get a quick definition of the right hand limit. So exercise, formulate the idea of left hand limit. Now let's prove one interesting theorem, and this is a theorem that is sort of taken to be a definition in high school. Let f from S to R be a function. Let A in S be a limit point. Then f is continuous at A. If and only if limit x going to A plus of f of x is equal to limit x going to A minus of f of x, is equal to f of A. Okay, assuming both these are defined. Now it can happen that A is not a limit point of S intersection open set A infinity, or it is not a limit point of S intersection minus infinity A. That can happen. So I'm assuming both of these are defined at the point A, then the function is continuous if and only if the left hand limit is equal to the right hand limit is equal to the functional value. Let's prove this. Let's prove this. Proof. Okay. Suppose f is continuous at A. Then what this says is mod f of x, so fix epsilon greater than 0. Then this just says mod f of x minus f of a is less than epsilon, there x is delta greater than 0, such that whenever mod x minus a is less than delta, okay, and x is in S. In particular, mod f of x minus f of a is less than epsilon whenever x minus a is less than delta and x is greater than a and x coming from S, right? I'm just taking a special case. I'm just looking at those points x which lie to the right of a by declaring that x is greater than a, right? In particular, this is true, and so is the fact that minus f of x minus f of a modulus is whenever x minus a is less than delta and x less than a, x in S. This is also true. Both will have to be true if you want the previous statement mod f of x minus f of a less than epsilon whenever mod x minus a less than delta and x in S, right? But this just says right hand limit at a is f of x, and this just says left hand limit at a is f of a at is f of a, right? These just follow from the very definition of limit. Excellent. So we have shown that continuity means that right hand limit at a is f of a, left hand limit at a is also f of a. Okay. Now for the converse, conversely assume right hand limit equal to left hand limit equal to f of a at a. Okay, then what do we have? We have for fixed epsilon greater than 0, delta 1 greater than 0, delta 2 greater than 0, such that mod f of x minus f of a is less than epsilon if mod x minus a is less than delta 1, x greater than a, and x coming from S. Similarly, mod f of x minus f of a is less than epsilon if mod x minus a is less than delta 2, x less than a, and x coming from S. I have just translated the left hand limit existing at the point A and the right hand limit existing at the point A into these conditions. So if you choose delta to be minimum of delta 1 comma delta 2, clearly epsilon delta definition of continuity is satisfied. So better to not write it like this. Clearly mod f of x minus f of a is less than epsilon if mod x minus a is less than delta, x coming from S. This follows immediately. Therefore f is continuous at A. F is continuous at A. Now, if it turns out that only one of these limits is defined, let's say this limit is defined, then it is sufficient to show that this limit is equal to f of a. Similarly, if only this limit exists, then it's sufficient to show that this limit, only if this limit is defined, it's sufficient to show that this limit is equal to f of a. Then the function will be continuous. Okay. So note that what we have shown is both the left hand limit and the right hand limit should both exist and should be equal to f of a for continuity. It just does not, it might be the case that f of x left hand limit is equal to the right hand limit of f of x at a, but they may not agree with the functional value. Let's see a few examples pictorially to see what and all can happen. Okay, so take for instance function which is minus 0 when x is less than or equal to 0, then 1 if x is greater than 0. This I denote by putting a circle here and a cross here to denote that at the point 0 the value is 0. Now here you note that the left hand limit exists and is equal to the functional value, but the right hand limit exists but is not equal to the functional value. Okay, more interestingly, you consider this example: 0 here, 0 here, but 1 here. Then both the left hand limit and the right hand limit will both exist, but not be equal to the functional value at the point. Okay, such a thing is sort of a removable discontinuity. What I mean by that is, you can make this function continuous by redefining the function at that one point A. It is possible to make it continuous. Whereas this function, the above, it has a jump discontinuity. It's not possible to redefine the function just at 0 to somehow make the function continuous. That's simply not possible. So you notice that the studying left hand limits and right hand limits could be very much useful in studying the points of discontinuity. And we will do this in great detail in a later module. Now I want to end with one more remark, which is essentially going to be an exercise. Remark. Suppose S is a set that has arbitrarily large elements. Then observe that limit x going to plus infinity of f of x. So f is a function from S to R. This is actually nothing but limit x going to 0 of f of 1 by x, where f of 1 by x is defined in an appropriate set with 0 as a limit point. Now I'm intentionally skipping the details. You can let me just write x going to 0 plus. That's what relates the whole thing. You can view limit x going to infinity as right hand limit of a function, slightly different function defined using reciprocals. It's a function f of 1 by x. And this limit x going to 0 plus f of 1 by x, you need to know where this function f of 1 by x is defined. That will be an appropriate set. I'm going to leave the details to you. So the definition of infinite limits is actually subsumed by the definition of one-sided limit. One-sided limits is sort of takes care of infinite limits also. We needn't have defined infinite limits separately. Similarly, we can deal with left-hand limits. Fine. So in the exercises, you will study this relationship in slightly more detail to understand what is the analogies between infinite limits and one-sided limits. This is a course on real analysis, and you've just watched the module on one-sided limits.